Okay, so as you can see, there's a long list of authors because this started as an Adobe internship that I was working on and continued as a collaboration between MIT and Harvard. So a recent Wired article brought attention to the fact that today we're on the verge of another revolution as artificial intelligence and machine learning turn the graphic design field on its head again. And the project that I'll describe to you today also contributes to this rapidly developing space of using machine learning in the service of graphic design. So specifically, we propose automated predictions on designs of regions in the designs that would be likely to attract observers' attention as feedback to help the designer refine the design in an interactive and iterative feedback. So we call this feedback that we provide the heat maps that you saw visual importance or importance maps. And this presentation will be about how we use machine learning to predict importance and the applications that we end up building on top of it. So what should visual importance look like? Well, to predict what will grab an observer's attention, our models should pick up on bottom-up features like fonts, colors, and styles that stand out. And this aspect alone might be accounted for by saliency models, and there are many saliency models out there. So just to show you a few, here's Itty Coke, Taralba, and Judd. But as you can see here, saliency doesn't quite capture the kind of feedback that would be useful within a design tool. And most saliency models don't generalize to graphic designs at all. So importance is more than just saliency. It also has to include knowledge about the semantics of different design elements. So whether something is a title or an annotation or a visual should affect whether or not we predict people will look there. Also what's important is how those elements are arranged. So their location should affect whether or not we predict people will look there within the context of the whole design layout. And having such an importance map can fuel a host of automatic design applications. And this includes retargeting, thumbnailing, and feedback within an interactive design tool. And I'll show you these applications today. But there's also a number of related works in this space as well. For instance, O'Donovan and colleagues predict a semi-automatic model for importance, and then they propose automatic redesigns and layout refinements. But importantly, behind the scenes of both models is a relatively slow optimization process that relies on design heuristics. So it's not going to generalize as well or be possible in very automatic settings. For their studies, they collected a graphic design importance data set, and I'll be using this data set in this project as well. There's also studies that make predictions about human perception, and they do this in order to either provide design feedback or to help automate the design process. And this work by Rosenholz and colleagues predicts visual clutter, while this work by Peng and colleagues predict eye gaze on websites to help optimize layout. But both models rely on very specifically structured input, so they're not going to generalize to broad sets of designs. And other work too has used saliency for design, but so far no dedicated and keyword generalizable model of saliency or importance for designs has been sufficient so far. But since predicting design importance is at the root of our applications, we need a definition and measurement for our models to strive towards. So I'll talk about three possible definitions of importance: as the locations where people look most, as the locations where people click most, and as the locations that people explicitly annotate as important. And I'll go into them in detail. So with regards to eye fixations, some of my earlier work investigated what makes a visualization effective. And I looked at the relationship between eye movements, human memory, and comprehension on a data set of data visualizations called MassViz. That's available publicly, and I'm also going to use it in the present work. In this work, we had found that eye fixations give us important clues about how people perceive visualizations, including what people remember and comprehend about them later on. And we used eye movement data to quantify the relative importance of different design elements. So for this, we took visualizations from the MassVis dataset that were annotated with title, legend, and the other elements as you can see on the plot on the right. On top of it, we overlaid the fixations of many observers into a fixation map. And what that allowed us to do is to aggregate the importance value, or rather the fixation map value per element into an importance score for that element. And by averaging over many visualizations from the MassVis dataset, you get the plot that you see on the left that sorts elements by importance of the fixation map. And of note is that the text, and especially the titles, are among the most fixated elements. And what's important about this is that in our comprehension memory experiments, we actually found that the title impacted significantly what people ended up recalling from memory later on, which means that these findings show that being able to predict eye movements has also important contributions to higher level reasoning and cognition, including memory. But eye tracking is an expensive and time-consuming process. It often requires many components, including specialized hardware and careful calibration procedures. And because it's not feasible at scale, we sought a way to crowdsource attentional patterns. So we designed an interface called Bubble View to collect mouse clicks on blurred visualizations. And as you can see here, as people click around, they de-blur small bubble regions at full resolution. As they click away, the previous region gets re-blurred, and the intention is to simulate foveal vision. At the same time, people are providing for us descriptions of the visualizations, and this is to make sure that their exploration patterns are meaningful. Now, when we have these clicks, we aggregate them over many observers, and what we end up getting is our importance maps aggregated from the clicks. And here, high values correspond to places that people are more likely to click. And we collected these click maps for 1,400 MassVis visualizations. And on a subset of visualizations for which we also had eye movements, we evaluated our importance maps collected using clicks against the eye fixation maps. And we found that despite some differences, as you can see here, at a very coarse level, the same design regions tended to be clicked on as looked on. So as before, as with the eye movements, we overlapped the click heat maps with the element segmentations to get per element importance scores, so we can compare it to how eye fixations rank elements by importance, and we found a very high correlation. So that tells us that people are tending to click and look in the same regions of a design, so we can use clicks as a proxy. Now, Donovan and colleagues also collected importance maps for designs, but they took a different approach. So rather than collecting eye fixations or clicks, they asked MTurk participants to explicitly annotate design regions that they found important, and no further definitions or instructions were given. But by aggregating these individualized binary annotations together, they ended up with importance maps, as you can see on the right here. And we also collected bubble view clicks for the same designs to see how the explicit importance maps compare to the bubble click maps. And we did some analysis to show that, again, at a coarse level, we rank elements by importance the same way as these explicit annotations do. But for modeling, we actually found that using the explicit annotations for graphic designs ended up yielding better predictions. And this is specifically because for graphic designs as compared to visualizations, having uniform importance across the design elements helped us with the downstream design applications like retargeting, which I'll show you later, because these explicit annotations allowed for better element segmentation. And with regards to model details, we ended up training two separate models. So one for data visualizations and one for graphic designs. And for data visualizations, we curated 1,400 images from the MassVis dataset, collected bubble view clicks for all of them. For graphic designs, we used the graphic designs from the GDI dataset of O'Donovan and colleagues, and we used the explicit importance annotations provided with the dataset. In both cases, we did an 80-20% split of the data, which means we trained on 80% of the data and tested on the remaining 20%. And having all of that data, we sought a way to associate visual patterns with the final importance scores. And we wanted it to be the case that no additional information would be required. So you can just feed the bitmap designs in, no extra annotations, no vectorized data. and we wanted fast real-time performance so that we can build this into interactive tools. And neural networks fit both requirements, and that's why we ended up using them for this project. So I'm going to include very few model details, but basically we used a VGG16 fully convolutional network that's used for semantic segmentation, but we adapted it for our task. So we have the network, instead of predicting segmentations, it predicts continuous distributions, or these importance heat maps, and we adapted the loss function accordingly to work for distributions. We found that a skip connection, as you can see in the bottom right, helped us refine our predictions, helped us refine the segmentations for the downstream design applications. Now at test time, our model takes input designs in bitmap form, which means that the models are agnostic to the encoding format, and we can run them on existing libraries of designs. So let's now take a look at some results. We have one network that produces importance maps for data visualizations and another for graphic designs, and I'm going to show you how we evaluated our predictions in both cases. So in visualizations, we compared our model to natural image saliency. We used JUD, which is a non-deep but popular model commonly used in saliency evaluation. It contains both low-level and high-level features. And we also compared to 3 very recent top deep neural network models of natural image saliency. Now, even in cases where text is detected by these models, and that's not always the case, these models don't know about the semantics of different text elements. What is the title, what is the legend, what is an annotation, and that ends up being crucial to predicting the importance, as I had mentioned to you at the beginning, where layout and element semantics matter. So quantitatively, across both metrics, cross-correlation and KL divergence, which are used for saliency evaluation, our model outperforms all of these natural saliency models. Here's some qualitative results, and I'm showing you here a range of good to poor predictions, so you can see our failure modes as well. Note how we locate the titles and legends despite their location on the design. But sometimes our model is distracted by brighter patches on the image, and this would be a similar failure case for saliency models as well. At a finer grain level, our predicted importance maps similarly rank elements by importance as the ground truth bubble clicks and eye fixations from before. But our model currently overpredicts the importance of titles. So it has learned this bias from the ground truth data, but there are cases when the titles are not the most informative element, and we need to train our model on more cases such as these so it can learn to generalize. So let's take a look at some results from graphic designs. For graphic designs, our model learns to distribute importance across visual and text elements. Sometimes we underpredict the importance of the text relative to the visual, and sometimes we overpredict. But which element is more important is sometimes design dependent and might depend on what is more informative in a particular design, and that might require higher level reasoning. For graphic designs, we compared to the model of O'Donovan and colleagues, which also produces importance maps for designs, but crucially at runtime requires ground truth annotations of people, faces, and text, which means it's not fully automatic. So here's a comparison of our model to O'Donovan's model, but because it's not fully automatic, we also compared to a model computed just using automatic features, and we note that both O'Donovan's models can take up to 10 seconds per image to compute importance. We do this in 100 milliseconds, so we gain about 100x speed up. And in numerical comparisons, we show that our model outperforms both O'Donovan's model and saliency, well, the automatic variant of O'Donovan's model and saliency. And now that we can predict importance on novel designs, a number of automatic design applications opens up. And I'll discuss these in turn next. So for retargeting, we may want to, say, take a poster and convert it automatically into a business card or website banner. And here I'm just going to show you how we can use our importance maps with no post-processing with a very simple approach. So we predict importance and we just crop around the region with highest importance. And we compare this very simple cropping with a common retargeting baseline using edge energy and saliency models, JUD and deep gaze. We evaluated the designs on mechanical Turk, and although we outperformed the simpler baselines, For this specific, very simple approach, we found that we perform similarly to deep gaze on this application. We also use the predicted importance maps for thumbnailing for visualizations. So, for instance, given this visualization as input, we again predict importance, and we find regions that we want to compress together into a thumbnail. So we merge these together, and just as with the retargeting, it's a proof of concept rather than a polished result. Here you can see 3 more examples of visualizations and their thumbnails. You can see that we pick up content from different regions of the designs, from the titles, the visuals, other large text regions. And we wanted to test the effectiveness of these thumbnails using a sample search application. So here, participants were given a target search phrase, a query, and they were asked to find the visualization matching it as quickly as possible in as few clicks. We found that using our importance-based thumbnails, participants completed this task in 40% less clicks than when we used the original visualizations but resized to thumbnail size. So we propose that these thumbnails can facilitate organization and retrieval visualization collections. We also wanted to test if our model generalizes to a finer grained setting with systematic variations in design. So we took a couple hundred design variants from the design improvement data set. We collected ground truth importance maps using explicit importance annotations on MTurk, and we tested our model on the same designs. Now, our model was never trained on such systematic design variants, but we noticed that it can nevertheless generalize and accurately predict how importance is affected by element placement or size, which gave us confidence that it could be used within an interactive design tool, such as the one I'm showing you here. So notice that here real-time predictions become crucial because a designer can now move around, resize, change the font and color of different design elements, and see how the importance is updated. At this point, our interactive tool keeps the designer in the loop by offering feedback. But for some design applications, we might want to take the designer out of the loop entirely for fully autonomous design. So maybe in the future, we can envision a system that will allow you to just dump elements onto a canvas like this and have possible redesigns assemble automatically, optimized for the various perceptual characteristics like balance and importance. But for now, we provide the perceptual characteristics, the perceptual predictions themselves, along with some initial prototypes that importance can be used for automatic applications like retargeting and thumbnailing. Remember that our models compute importance in about 100 milliseconds per image, so they can be built into real-time applications. And if you would like to use them, our code, model, and other data and details are available on our website. And we're also going to be at the demo session showing off this design tool. Thanks for your attention.
Please bring your questions to the microphone, and if you could state your name and affiliation first.
Hi, Steve Feiner, Columbia University. This is really, really neat stuff. You mentioned in the talk that there had been some other work that required the recognition of faces, for example.
Of faces?
I thought you said faces.
No, we did visualizations, data visualizations. Okay. Go on with your question. Maybe I'll be able to answer it.
In any case, I was wondering, since things like this might actually have things that are very salient to people like faces, had you thought about using things that automatically recognize those faces to be able to go and contribute to an estimate of what people are going to be looking at?
Well, so I have tried working with faces a little bit, so I'll kind of answer your question this way. The recognition memory experiments we did is for data visualizations. They sometimes include faces and people look at faces, but in terms of looking at individual faces, we actually did run eye tracking experiments trying to see if from eye movements we can tell if people recognize faces. It's a very hard problem, so from the eye movements you can't do that.
No, I was thinking there are ways to automatically find faces in imagery.
Oh, to do face detection.
Using face detection systems to be able to go and contribute to the estimate that you're going to have of where people are going to be looking.
Right. So actually the neural network that we use for predicting importance is pre-trained on natural images. So it has this implicit knowledge about faces and text and other objects built in. So we're actually leveraging that, and it's actually it's very powerful because of that. If we wanted to tune it to be better at faces, we could do some learning strategy where we feed it more faces specifically, direct its attention to the faces or the text or whatever else you're interested in, and then retrain it to predict importance. So it does have that built in almost implicitly, but through the pre-training.
Okay, thank you.
Yeah.
Hi, great. Lydia Chilton, Columbia University. So this is really fantastic. I'm excited. Particularly, heat maps can be really important in the design feedback process. Often, when I design, I start with a sketch, and I'm wondering if the models you've trained, would they apply